Hello guys, my name is Balkrishna Srivastav and welcome to Code with BK. In this video, we write a Java program to model complex number in a class using OOP principles. So before we begin, it is a request to please subscribe to my channel, because out of 100 viewers, only 1 or 2 are subscribed and a subscription is very important. So please subscribe to my channel. So we need to create a class that will model complex number, and we'll try to add as many as functionalities to this complex number class possible. I have taken another class, test complex number. In this I have a main. Here I am going to test everything that I code about this complex number class. Okay. So we all know complex number z is equals to a plus ib. Okay. Where a is the real part and b is the imaginary part. Okay. So since a complex number has two parts, real and imaginary, I am going to take two integers, private int real for the real part and private int imaginary for the imaginary part. Okay. And obviously these can be doubles as well, but we'll look at that later. Okay. And to create a complex number, I will add a constructor which is public. Okay. This takes the real part and the imaginary part as well. Okay. Right. I said this real to real and this imaginary to imaginary. All right. So let me create a complex number object. I'll say complex number z1 equal to new complex number. I'll pass 2 as the real part, 3 as the imaginary part. But how do I print this? So I'm going to override the toString function so that I can represent this class as a string. That is, I can represent this complex number as a plus ib. So I'm going to say public string toString, and we know all classes have a toString implicitly because toString is a part of the object class, and object class is the superclass of all classes. Okay. And when we are overriding toString method, we make sure that this is the method signature. Okay. That it is public, return type is string, and this is the exact method name. Okay. So I need to represent complex number as a plus ib. So I'm going to say return blank plus real part. Okay. Plus space plus. Okay. And plus I plus and imaginary. Okay. So now I can say out z1 equal to plus z1. Okay. So when I print z1 here, toString method is called implicitly. So when I run this, I get 2 plus 3i. Let me make it 3i. So I'll say plus plus and plus, and I'll move this imaginary part here. Okay. So when I run this, 2 plus 3i. Okay. Let me take another complex number. I'll say 3 comma 4. I'll name this z2. Okay, and I'll print c2. I'll say 3 plus 4. Okay. All right. So what if we have a real number that has only the real part and not an imaginary part? So I will write another constructor. Okay, that just takes the real part. Okay, and it calls the first constructor passing the real and imaginary part as 0. Okay. So when I create a complex number z3, I will just pass say 5. Okay. And I'm going to print z3. Okay. So z3 is okay. So I don't want the imaginary part printed if this is 0. Okay. So in my toString, I'll say if this dot imaginary is 0, return blank plus this dot real. Okay. That is, if my imaginary part is 0, I just want the real part. Okay. So when now I run this, for only the real parts I get this. Alright. Now what if I want a complex number which is 0? I can add a default constructor. I can say takes no parameters, passes 0 comma 0. So when I create z0, okay, which is going to be calling the default constructor, which is basically a 0. So when I say z0, okay, let me run this. So it is 0. Alright. Let me add another complex number. I'll say z4, I'll say minus 2 and minus 3. Okay. I'm going to print z4, z4, z4. Okay. Run this. z4 is minus 2 minus plus minus 3i. So I don't want this extra plus symbol. So what I'll do is else if this dot imaginary is less than 0. If the imaginary part is less than 0, I will not print this extra plus symbol. So I'll copy this, return it here and remove this plus part. Okay, so when I run this, I get -2 -3i. Alright, okay. Or if you want the minus symbol in the center, you can say return this thing, okay, add a minus symbol and we will say -1 into, okay. You're not actually changing the imaginary part, you're just multiplying it by -1 because you're printing the minus symbol separately. Okay, so when I run this, I have -2 -3i. Okay, all right. You can choose any of the outputs you want. All right. So this is creating a complex number z equal to a plus ib. This is creating a complex number z equal to a. This is creating a complex number z equal to 0. Okay. Then we have something called a modulus of the complex number. So I'll say public double modulus, okay, which is equal to underscore a square plus b square. So I'm going to return math dot sqrt, okay, math dot pow plus math dot pow. Okay, so real to the power 2 and imaginary to the power 2. So under root of a square plus b square. Okay, so you can say here mod z equal to sqrt rt of a to the power 2 plus b to the power 2. So I will calculate mods for these three values. So I'll say mod z1 is z1 dot modulus, I'll say z2 and z3, remove this, mod z2 mod z3 mod z2 mod z3, and I'll say z4 as well. Okay, 0 is going to be 0, so I'm not going to print the modulus of it. Okay, z2 is 5, z3 is 5, z1 is this and z4 is this. Okay, all right. Then we have something called the complex conjugate of a complex number, so which is denoted as z bar. The bar symbol is on the top of z, but I'm tapping it like this, is equal to a minus ib. Okay, the imaginary part is basically set to minus symbol. So I'm going to say public complex number, because the conjugate of this complex number is another complex number. I'll say the function as conjugate, okay, and it will return a new complex number, okay, with real part as it is and imaginary part as negative. Okay, and then I'm going to print complex conjugates. I'm going to say z1 bar, okay, dot conjugate. Okay, I'll say z2 z3 z4 z2 z3 z4 z2 z3 z4, running this. So z1 bar is 2 minus 3i, z2 bar is 3 minus 4i, z4 bar is minus 2 plus 3i. Okay, now we add some more functions to it. The first one I'm going to do is add. So if I have z1 equal to a plus ib and z2 equals to c plus id, okay, then the sum of these two, z1 plus z2, is basically you add the real parts and add the imaginary parts. So you say a plus c, add the real parts, plus I, you add the imaginary parts, b plus d. Okay, so I'll say public complex number. The return type of this is going to be a complex number because you're adding a right hand side complex number to this object. Okay, add RHS to this object. Okay, so I'm going to return a new complex number. Okay, the real part is going to be real plus RHS dot real and imaginary plus RHS dot imaginary. Okay, so I'll say complex number z5 is z1 dot add z2, z6 is z3 dot add z4. Okay, and I'm going to print z1 plus z2 equal to z5. Okay, and similarly z6 is equal to z3 plus z4. Okay, and you can see the state of the objects is not changing. When RHS is sent here, neither the current object, this object, nor this RHS object, the real and imaginary parts of these are not changed. Okay, we are creating a new complex number with the real and the imaginary part calculated as sums of the individual real and imaginary parts and returning it. Okay, so this is equal to, okay, so z1 plus z2, z1 is this, z2 is this, 2 plus 3 5 and 3 plus 4 7, and z3 plus z4, 5 minus 2 is 3 and 0 minus 3 is minus 3, which is this. Okay, all right. Similarly, we can add the subtract function. Okay, it is very similar to add, you just subtract the individual parts. So if z1 is a plus ib and z2 is c plus id, z1 minus z2 is a minus c plus I b minus d. Okay, so instead of adding the individual parts, we subtract them. Okay, so similarly, I am going to say z7 z8, okay, dot subtract z1 minus z2, z3 minus z4, so z1 minus z2, z3 minus z4, z7 z8. Okay, z1 minus z2 is z7 and z3 minus z4 is z8. Running this, z1 minus z2, 2 minus 3 is minus 1, 3 minus 4 is minus 1, and z3 minus z4, 5 minus 2 is 7, plus 3. Okay, all right. Then we move on to the multiply method. So if we have z1 equal to a plus ib and z2 is equals to c plus id, then z1 plus z2 is equal to, there is a standard formula for it, let me tell you that. Okay, we add multiply. Okay, all right, we create this in, okay, it is equal to ac minus bd plus iad plus bc. All right, and this is a very standard formula. So this is what we do, we calculate AC. A is this dot real into C, which is RHS dot real, minus B, which is this dot imaginary, into D, which is RHS dot imaginary. Okay, this is the real part. Now second argument is going to be the imaginary part, A, which is this dot real, into D, which is RHS dot imaginary, plus B, which is this dot imaginary, into C, which is RHS dot real. Okay, multiply RHS to this object, subtract RHS to this object. Okay, so I am going to say complex number z9 z10. Okay, z1 dot multiply. Okay, copying this, z1 into z2, z3 into z4, z9 z10. Running this, z1 into z4 2 is this and this is this. Okay, let's see what we get when we multiply by 0. So I say z1 into z0. Okay, so I'll say z1 dot multiply by z0. Okay, you should get a 0. Let's see, it's a 0. Okay, either way around, z0 into any other value, say z4. Okay, we are not actually changing z4, we are just multiplying z0 by z4 and getting the final product into a new complex number object. Okay, this is again 0. All right, so we have covered add, subtract, multiply. Let's look at divide as well. So if I have z1 as this, okay, z2 as this, then z1 by z2. Okay, this is again a standard formula, and I will change this to divide RHS to this object. Divide this by RHS basically. This is basically equal to this, AC plus BD by C square plus D square plus I BC minus AD C square plus D square. And since we are dividing by C square plus D square here, if we don't change the data type of the numerators to a double, we might get zeros. Okay, so let's change this to double. Okay, basically I can add a constructor double and double. Okay, and maybe you can comment this out, and instead of this you can add double real, comment this out. Okay, all right, rest of the parts remain the same. Okay, so let me run this. All right, so you see now we get 2.0 plus 3.0 I instead of 2 plus 3 I, 3.0 plus 4.0 I. I don't want this 0.0 if the decimal part is 0. I just want the whole number. If it is 2.0, I just want 2. If it's 3.0, I just want 3. If this is something like this, okay, I am okay with 3.6 or something then. So how do we change the printing to 3 instead of 3.0? I will go to my toString function. So in my toString, I'll take toString, real part, that is going to print the real part, and string imaginary part, that is going to print the imaginary part. Okay. If the real part is a whole number, okay, we do not print the 0.0. So how do we check if this is a whole number? We'll say if real percent 1.0 equal to 0. Okay, this checks if there is no decimal part to it, it's a whole number. Then what we do, real part is blank plus int of real. Else if the real part has decimal points, so you simply say blank plus real. I do the same thing for imaginary. If the imaginary part is the whole number, we don't put, so we say if imaginary percent 1 is equal to 0, imaginary part is int, otherwise it is as it is. Okay, all right. And instead of printing this dot real, we print real part. For 0 we print the real part. Okay, but here if I use this, I cannot multiply by -1. Okay, and similarly real part plus imaginary part. Okay, okay, now let me run this again. So you see 2 plus 3i, 3 plus 4i, minus 2 minus 3i. But now this minus symbol is not in the center between two spaces. It's as a minus sign of this imaginary part. Okay, you can bring this in the center like this, no big deal. So we were able to change the types of real and imaginary to double, and still we get a pretty output. Okay, let's complete divide. So I need to code AC plus BD upon C square plus D square as the real part and this as the imaginary part. So we get Z2 mod square, which is basically C square plus D square, C square plus D square. Okay, then we get the real part, imaginary part, we return the new complex number. Okay, so when we print here, we say maybe, okay, so now we test Z11, Z12, 1 by 2 and 3 by 4. Divide Z1 by Z2, Z3 by Z4. Okay, Z11, Z12. Alright, let me print this. Okay, this plus this I and this plus this I. So for values with decimal places, we get the entire value, and for values with no decimal places, we get integers. Okay, let's see division by 0. So I will say Z1 by Z0. So I'll say Z1 dot divide by Z0. Okay, let's see what we get here. So we get a nan, not a number. Okay, so we need to handle division by 0 here. So cannot divide if RHS is 0. Okay, so you can check RHS dot real equal to 0 and RHS dot imaginary equal to 0, or you can write another helper function. I'll say public boolean is 0 to basically check if this complex number is a 0. So return this dot real equal to 0 and this dot imaginary equal to 0. Okay, so if RHS is 0, okay, I'll throw an exception, new arithmetic exception. Okay, divide by 0 is not allowed. Okay, so when I run my main, I get exception here. This is here. Okay, so I'm going to comment out the line that is giving me exception. Okay, so we are done with almost all the functionalities. We can add one more function, which is public boolean equals, to check if two complex numbers are equal or not. Okay, so I'll say if other is null, I simply return false. Okay, if other is instance of this object which is complex number, this type which is complex number, I will compare, otherwise I'll say return false. Okay, and this is a very standard way of coding equals method, and equals method is being overridden here. because equals method is a part of the object class, which is the super class for all classes. Okay, so I get complex number from this given object. I'll say that equal to complex number other. Okay, I'll say return this dot real equal to that dot real, and this dot imaginary is equal to that dot imaginary. Okay, so I need to add 1 plus 1i to this 2 plus 3i to make it equal to 3 plus 4i. Okay, okay, so let me check z1 equal to z2. I'll say plus z1 dot equals z2. Okay, obviously this is going to be false. Okay, I will say plus 1 plus 1i, okay, equal to z2. Z1 dot add new complex number 1 comma 1, okay, and then check if it is equals to z2. Okay, so z1 is 2 plus 3i. I am adding 1 plus 1i to it, so 2 plus 3i plus 1 plus 1i should give you 3 plus 4i should be equal to z2. Okay, running this, true. Okay, all right, so if I subtract 5 from z3, it should be equal to 0. So I should say 5 from z3 minus 5 equal to z0, as that is right, z0. Okay, z3 subtract 5, which is new complex number 5 dot equals z0. Okay, let me run this, true. All right, and if you want to have more precision when you are comparing real and imaginary part, which are double values, you can use double dot compare. Okay, this dot real and that dot real, okay, equal to 0, double equal to 0. Okay, so this is recommended when you want to have high precision comparison. Okay, this dot imaginary, RHS dot imaginary. Okay, so this was a class that can model a complex number and do some very basic operations to it. Okay, more than basic operations to it. All right, you can think of more functions to add to it, but this basically represents a complex number. Okay, running this final version again. Okay, all right, so this was the code to model a complex number using O principles as a class. Okay, and I hope this was helpful. So if you like this video, if you found this helpful, please do subscribe to my channel. And if there was something that you did not like about this video, please just don't press the dislike button. Please also let me know in the comments what was it that you did not like about this video, so that I can improve in my further videos. All right, and you can also mention in the comments if there is a question you want to solve or if there is a concept you want to discuss. Thank you.